Okay, today we're going to be talking about stars. We talked about planets, we talked about the sun, and now we're moving on to stars. We're expanding our horizons. So we're going to talk about classification of stars. Lots of different types of stars. They're largely based on how big they are and also their temperature. And those two things make all the difference. So we're just going to talk a little bit though about color. The color of stars and how that affects their classification. So let me zoom in on this. We're all used to my great production at this point. We're all doing the best we can here. Okay, so what do we have here? What are we looking at? Well, let's picture an electric stove, or picture if you have, say, a red hot poker or a horseshoe and you put it in coals, like if you have a barbecue or if you have a stove. When you first turn this stove on, this is, the older electrics, the burners on top. Well, you know they're warm, you can't see anything, but you know they're warm. You turn it on, you'll see a light and you can feel the heat, but you can't see anything. Eventually, it'll start to turn red. So that's interesting. So it had an infrared. We can feel infrared with our skin, but we can't see anything. Then eventually you can see it. Well, it's gotten hotter. And we also know that it's hotter, so we don't want to put our hands as close. So it's radiating more heat, more and more heat. Now we know if we kept it going, it would go from red, it could start turning like an orange, right? And for stoves, that's about as hot as they'll get. But if you have, say, a horseshoe that you put into coals, it would turn red, then orange, then eventually like a white hot, and then even blue if it didn't start to melt. Well, that's represented by these curves here. So here is something at 5,000 Kelvin, right? Kelvin goes down to 0. So 5,000 degrees Kelvin. And it has a peak temperature where it's red. Well, notice it also, well, we know it's given off in the infrared. We can't see it, but we can feel that with our hands here, right? So we know that there's infrared here, right? We already studied about light, so we know that. And then red is the first color we could see. Well, if it kept getting hotter, it would eventually turn orange, right? Well, what if we heated it up to, and this here is intensity, so it's just how much heat is coming out altogether. So intensity on this side, here is wavelength. Well, we're used to wavelength. Remember, the longer the wavelength, the less energy, the shorter the wavelength, the more energy, right? We studied all that. Radio waves are way out here, and X-rays will be way out here someplace. Ultraviolet will be here, but the visible, right, it's the colors of the rainbow. If it got even hotter, well, it wouldn't be red anymore, it would be white hot. Well, Felix, that looks green to me. Well, that's because our eyes, the way the rods and cones are, I don't know, maybe because of the grass or something, the way we evolved. But when something is green hot, we actually see it as white hot. That's just our eyes, right? So here it's giving off radiation in the green. We see it as white hot, and it's even hotter. We could not get our hands closer to this thing. Here, it's at 7,000 degrees, and now it's turned blue, even purple. So it's super hot, and notice the intensity is way more intense. So these are called black bodies. You know, they're things like old-fashioned light bulbs, really old-fashioned ones. We turn red just for a bit, then they turn white. An incandescent bulb. Incandescent means you get light from heat. Right, so if you had a horseshoe in coals or in a fire, right, a burner, or in your toaster, it'll turn red, right? So those are things that are examples of a black body. Don't worry about the name. It's derived from a German name. But it's just, and they have this temperature. They just do. And they'll have a color associated. So, and then they have a curve, a very special curve. It's a kind of an uneven curve. If you measure these things, and scientists do, if you measure different objects like that, they have a curve where where way out here it's giving off, yeah, a little bit of, well, of course there's infrared, we can feel that, but way out here, yeah, there's a little bit of maybe microwaves, just a little bit. Here it's giving off some ultraviolet, yeah, you didn't know that, but it is, right, a little bit. So why are we talking about this with stars? Well, it turns out the surface of stars approximate black bodies. They act very similar to a horseshoe that would be in hot coals or your burner on your stove. Remember, stars are a gas, but there's a lot of gravity there. The gas is very compressed, so it acts like, kind of like, you know, molten lava. We've seen Hawaii, where the lava is coming out of the volcanoes and flowing down, going to the ocean. It's red. Well, it's a liquid, but it's very, you know, dense. Well, the surface of stars, it's a gas, but it's dense because there's a lot of gravity. So it acts like these black bodies. What it means is that if you see a red star, it's cooler than a yellow star. Our sun is a yellowish-white. It's 5,800 degrees at the surface. And here we're talking about surface temperatures, not the temperatures inside where the thermonuclear fusion is happening. Let me check the camera, right? It's all professional here, folks. Yeah, okay, hopefully you can see that. So, right, so stars, the surfaces of stars act a lot like these things we're calling a black body. Right, black bodies are like metal, molten lava that comes out of volcanoes. That's like a black body, right? Right, the burner on your stove. You look inside a toaster, right? So those are things that act like, right? What's not a black body? Wood is not a black body. Styrofoam, paper. No, it's like metal or rock type things, right? Well, surfaces of stars approximate that. So what it means is when you look and you see kind of a red star, it's cooler than a blue star. So it's a rough indicator. So that's important. But, so temperature is one of the things that's a big indicator of stellar classification, right? So let's, in our book, I happen to have our book right here, right? On page 601. It talks about spectral classes for stars, right? So this is our book, spectral. Well, we know all about spectroscopy. I did a video on that. So the book talks about it. There's another video. So we know all about that. So one of the characteristics for classifying different stars is their temperature, okay? So let me get to another PowerPoint chart. We'll go to this one. So here, these are different types of stars. O, B, A, F, G, K, M. They used to be, there's a lot of history to this, they classified stars alphabetically a long time ago. Well, then they made more discoveries and more discoveries. But people were already used to the classification system. So it ended up like this. So we kind of ended up like this. There's a kind of a silly story on how people used to remember this. This is back before the world was so politically correct, right? But a little bit of history here. People used to remember the classification of stars. It was O, be a fine girl or guy, kiss me, right? So it's just a little goofy little mnemonic, just something to remember it, right? So type, and this is on page, in your book, this is also on page 601, right? In your book, it also shows the color. So notice that type O stars are about 40,000 degrees. They're the hottest, right? They're blue, okay? So make sure you read this in your book. Type B stars are about 20,000. Type A stars, type G stars, 5,500 degrees, right? 3,000 degrees. So type M stars are red, K stars are orange, G is yellow. Our sun is a type G star, so it's classified as a type G star. Okay, so this is, if you look at the stars that are visible in the sky, study the stars, they have been classified in this order. And there's another thing that's very important in classifying stars. It's also their size, just how much stuff they have. You know, the more stuff they have, of course, they have more gravity, but it also affects their characteristics. So this is a graph called the HR graph, named after two scientists, Hertzsprung and Russell. HR diagram. It's the most important diagram in astronomy when it comes to stellar classification. In your book, this is on page 641, right? They have notice the book does a really good job color coding. So it shows that the hottest stars are blue or even purple, right? And then they go down, down, down. Here it shows green, right? We don't see green really. We would see these stars as white because of our eyes. And here's yellow stars, right? Our sun is a yellow star. And then red for the cooler stars. But notice it's kind of backwards. We're used to curves where maybe you would start at 0 and then the numbers get bigger. On this curve, so we're used to maybe, yes, I'm going to show this one here. So here's the temperatures on the bottom. It's just like the one in the book. And you can see here, it's kind of going blue, purple, yellow, orange, right? It kind of, the book shows it much more distinct. Yeah, so let me just go down a little bit. Make sure we can see that well. Okay. So this is a graph. Here you have the luminosity. And what it is, the sun, they're calling the sun 1. If things are brighter than the sun, they're higher than the sun on the curve. If they're less than the sun, they're lower. So we're used to our sun, right? You can go outside, you can feel the heat, right? You can see how big the sun is. Remember, don't look at the sun. But we're used to our sun, so we're using our sun as the standard. And then here we're classifying stars that are less bright than the sun and that are more bright. Then the temperature, they do it backwards, right? It's a backwards thing, where they start at the higher temperatures and then they go down. You can do anything, you know, graphs are for people, so they work for us. So this word here is temperature, if you can't see that. This is temperature. So it starts higher and it goes lower. And it's just like we said, the hotter stars are purple, blue, right? Here it's white. So here they're not showing green, here they're showing white, which is what we see because of our rods and cones and our, like on Earth we see the planets as green, but when it's a bright hot object we see it as white. But the wavelength is the same as for green. Then here yellow, and here's our sun. Our sun is right here on this graph. It's yellow. And then red. So it's just like in the book. Make sure you read this in the book, right? Okay, so the Hertzsprung-Russell diagram is the most important diagram. Here you have how much energy is coming out of the stars, or the luminosity, or you know, so it's all the heat and all the different wavelengths that are coming out. That's what this is, and this is the temperature, right? So all stars that are here, say here at 3000, they would all have the same temperature. But here is how bright they would be. It's how much energy is coming out. Well, if they're the same temperature, what would be the only difference that would make something the same temperature have more light? Well, it's just its size, if it's bigger, right? So here you have red giants up here. So there'll be red, so they're cooler stars, but the bigger ones, well, you can see them, they're brighter. If you had one candle and it was burning at a certain temperature, okay, and then you had 100 candles, you know, kind of closely spaced, well, they're all going to have the same temperature. It's the same type of candle, but you would be able to see the 100 candles from much farther away because there's more light coming out. It's bigger. It's a bigger group of candles. So it's the same with stars. If you have, even though they're the same temperature, the bigger ones you're going to be able to see, right? So here you have red dwarfs. That's a good name, red dwarfs. They're little stars. Here you have giants, and these are the red giants. So that works out. That's pretty easy, right? Then here you would have white dwarfs. So these are smaller stars. and then here you would have giants again. So the smaller stars are going to be just less luminous than the bigger ones of the same temperature. But what is so special about this curve is that it actually, if you classify them this way and set this up, it shows stars' lifetime. This line down here is called the main sequence. This sort of white is called the main sequence, right? When you're born, you're a baby, and then you're growing. Then around 18, you pretty much stop growing, and we say you're an adult. Well, when I was between 18 and 21, I grew about another inch. So at 21, like you're really an adult, right? United States, we say, yeah, 18, you're almost an adult. At 21, you're really an adult. Pretty much just because you stop growing, right? That's what happens. So stars, when a star is forming, right, all this stuff is falling in, the star is forming. Eventually, there's enough stuff. Thermonuclear fusion happens just because there's so much stuff, it's able to push atoms close together and then fuse, because the protons in the nucleus, they're repelling, but there's so much gravity, so much pressure, it forces them together, and you're forcing hydrogen into helium, right? Thermonuclear fusion starts. Well, eventually you reach a balance, and I talked about this in the other video, where you have thermonuclear fusion going on at the core. So that heat is expanding, but gravity is pushing it, and eventually it settles into a nice balance. Our sun is at that balance. Our sun is just pretty much always the same. It varies a little bit. You know, it has solar flares and stuff, but pretty much the same energy is coming up. It has that balance where it's quite evenly burning it's quite evenly burning hydrogen, converting it into helium, and it's balanced with gravity. And of course, life has been able to evolve on our planet, and we have this nice steady stream of heat, and we exist, right? Eventually the sun, so that is when stars are in their main sequence. It's when they are burning, I shouldn't say burning, it's when they're undergoing thermonuclear fusion, and they're converting hydrogen into helium. And then also in the bigger stars, you can convert helium, you can fuse helium into heavier elements, and then so you can keep fusing heavier elements into even heavier elements, but you just need a bigger star that has more gravity that's able to do that, right? So when stars are in their adulthood, the main part of their life, they're on what is called the main sequence. Test question, right? The main sequence is where stars live out the bulk of their lives. It's when they're steadily fusing, they're using their fuel, primarily hydrogen, converting it into other elements. Now eventually you start running out of hydrogen. Well, that's kind of like when humans start to become elderly, where they're no longer on the main sequence where they're good, vibrant, healthy adults, right? Eventually you start to become elderly, where you're just not, you need a cane, you're walking slower. We know what it means, right? We know what that means. So now they move off the main sequence, and they go. So that's what these other stars are. These are stars that are not on the main sequence. Are either they're young stars that haven't gotten onto the main sequence yet, or they're older stars that they're nearing their end of life, and it's because there's no longer a lot of hydrogen available to fuse into helium, and so the star is starting to die. They move off the main sequence. That's why this curve is so important. So we can recognize these stars. We can recognize stars that are on the main sequence. Remember, we can tell what elements and compounds are in the stars by using spectroscopy, right? See my other video and the other videos that I posted, and read the book. So you know about that. We know we can do that, right? So that's the power of this diagram. So test questions might be, well, what is on the main sequence, right? Well, that's when stars spend the majority of their life. They're kind of their adulthood, right? If they're not on the main sequence, they're either juvenile stars that are still growing and they still have growing pains, and they're not fusing their hydrogen into helium very evenly, right? Eventually they will. Then they're on the main sequence. Once they start dying, once they start running out of hydrogen, then they start moving off the main sequence. So that's the power of this. So it's temperature, right? And then we've had a number of videos that talked about different types of stars. So white dwarfs, hot, smaller stars here, red dwarfs, hot or cooler, and then up here the stars are more luminous, and they have a higher luminosity. There's more energy coming out. They're just bigger, right? So the bigger stars are more luminous, and then of course if they're hotter and big, they can be really luminous. Cooler stars are red, and then the hotter stars are blue. So this is the Hertzsprung-Russell diagram. Very important diagram in astronomy. And then here is the classification letters again. O, B, A, F, G, right? O, B, fine girl or guy, kiss me, right? From back in the olden days where that wasn't, they weren't so politically correct, and people just thought that was a cute little thing to help remember. So okay. So make sure you know that. Make sure you read about this. Page 641, stellar classification. So if you look at stars in the sky, Betelgeuse, for instance, is in a constellation of Orion. It's visible right now, this time of year, when the sun goes down. It's been varying in size lately. So it's a big red giant. It's a dying star. It's been varying in size. So it's having a lot of trouble. Its brightness has been getting lighter or dimmer and brighter. So it's actually moving up and down recently. This has been only the last couple of years it's been doing that. So it's dying. It's having a lot of trouble, right? Then Rigel is also in Orion. It's a bright, like, blue star. Even me with my old eyes, I can see. A lot of times stars just look white, but if you look at Orion, when you see once you see a red star closer to a blue star, then you can see the colors. It helps to see them near each other. So you can do that in the constellation of Orion. Just look to the south. Once the sun goes down, this time of year, you can see Orion. Very, very distinguished. It has the four main stars and a belt in the middle, and he has like his sword sheath, right? That's if you look at the picture of what Orion's supposed to be, the swordsman. Okay. So that's your HR diagram, the Hertzsprung-Russell diagram. Oops. Of course I bumped into the camera. And that's all there is, folks.